Okay, a study of sleepwalking or nocturnal wandering was described in Neurology magazine, and it included information that 29.2% of 19,136 American adults have sleepwalked. Would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? Use a .05 significance level to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 30%. Okay, we've got a couple numbers going on here, and it's not completely or terribly apparent what is what here. This is meant to be a p-hat symbol here, but the 29.2% of 19,136, that percent is derived from our sample of 19,136 American adults. So this information is from our sample, so that's how we know that this is our p-hat or our sample proportion. The reporter is estimating that he could say that less than 30% of adults have sleepwalked based on that 29.2%. So the real question here is that our sample is telling us 29.2%. That sample statistic is a pretty good point estimate of what we think the true population proportion of sleepwalking adults would be. But it's not going to be exact. There's going to be a margin of error. So basically we were trying to figure out, is that 0.8% from 29.2 to 30, is that within that margin of error or not? With a really large sample like this, it possibly could be. That's really what we're getting at here. So we're wondering if he can round up to 30 and say safely fewer than 30%, or is that just outside the range? So getting started here, our claim, the other thing that we need to be aware of is that the proportion of those who sleepwalk is less than 30, that's less than phrase, or fewer than 30%, is really a heads up that we are dealing with the probability in a tail. So our first step is looking at that claim. The claim is that less than 30% of the full population of adults have sleepwalked. We can write that in numeric form or algebraic form as p is less than 0.3. That's our population proportion, is what we're estimating or taking a look at. I'm not going to ask for those two things on a test, but that might help you get yourself squared away. Okay, so here's where we need to start in, and these are the things that I would be looking for on an exam. HO, again, is that null hypothesis. That's always going to include the equality sign. So we're going to state right out of the gate here that the population proportion is equal to 0.3. Our alternative is where we're going to look at that tail, is that the population is less than 0.3, and that happens to be what our claim is. So if you can get yourself squared away, that's going to help lead you there as well. The next thing you need to take a look at or take note of is our confidence level is 95%. That is going to be a complement to the significance level, which was given to us as 0.05, so that's really repeating basic information there. I'm making note that this is a left-tailed test, and I got that because we have this claim, or our alternate is less than 0.3, so that's our left-tailed test, and the z-score that is associated with 5% in a left tail would be negative 1.64. You would get that from the formula page. Looking at this here, we're looking at an alpha of 0.05 in one tail. Because it's the left tail, it's going to be negative, so we got that from the second line there. The other thing is if you remember in class, we worked on this activity just so that we could see where these probabilities and tails and the z-scores were all situated. We're looking at a left tail test, so we're going to be looking at that first column. We want all 5% in the probability of error in that lower tail, and the z-scores that is associated with that we discovered was negative 1.6. Now take note, later in this problem we are going to write a confidence interval. Our confidence interval is always a two-tailed event, and when we look at the two-tailed event, where we have 5% in a tail is with a 90%. So you can see we've got negative 1.64 here, and we have it here. This is the curve that we're looking at and utilizing in a left-tailed hypothesis test. This would be the curve that we would be looking at when creating a confidence interval, where we would have all 5% in one, I should say, when we would have 5% in one tail, 5% in the other tail. So that's just getting our bearing between those two things. Okay, so back to our problem here. So we've got all of that down or nail down for us, our next step is to take a look at our test statistic. So writing in our information, again, here's our formula. Remember, p hat comes before the population proportion. So we're going to plug in the information. I need to write this percentage as a decimal minus what we're projecting the population proportion to be. And again, remember that in this formula, our test statistic, we're putting in our data or our P and our Q that has to do with our proposed proportion over our sample size. We end up getting a very, very small z-score. So just looking at that, we can, comparing this here visually, we don't really even need to look at a curve. We know that that is much smaller, but we want to definitely take a look at our three methods and make sure that they all jive. Here we've got our critical value method. When we draw the curve, put the z-score of negative 1.64 in here. What I've shaded is the 5% that it would be in the rejection zone, and we can see our test statistic definitely falls in that rejection zone. The other thing is we can look at our p-value. I didn't pull up the normal distribution, but you would look for this test statistic, negative 2.41 in the first column, top row, and you would find that that would correlate to a probability of 0.008. We know that that's very low, so that jives, that's low. And again, the whole idea that if the p is low, the null must go, all works. Going back to our confidence interval method, when we plug in the confidence interval, again, we're looking at p hat. Our p hat was 0.292 from our sample. We're going to be using that z-score that correlates with 90% confidence interval. That would get 5% in each tail, and that z-score would be a plus or minus 1.64. So we see a repetition of that, but it's plus or minus in this case. In our confidence interval, we're plugging in the p and the q that is derived from our sample statistic. So we plug all that in and we get this interval here. And this is really interesting in that it was a close call, but you can see the population proportion that we were testing, 0.3 or 30%, does not fall in that interval. It's close, but it doesn't fall in there. So that again tells us that we have to reject the null hypothesis. We can't possibly support the null hypothesis when it's not even included in our confidence interval. So I made a note here that, again, when you go to StatCrunch, which I'm going to show you here in just a bit, it's not going to know that you will need to identify a 90% confidence interval when you're doing the confidence interval in StatCrunch. So our choice, all three methods support that we will reject the null hypothesis. There is sufficient evidence to support the claim that less than 30% of adults have sleepwalked. In other words, there is sufficient evidence to support our null hypothesis. Okay, now we need to go into StatCrunch, and I'll show you how you do this particular problem here. I'm going to get back up to this point here. Open that. Okay, so I'm going to go into StatCrunch. Now the part that we're into now is we are no longer in calculators, so we're going down to proportion statistics. We have one sample. We are dealing with summary information, so I'm going to open that up. Now the thing here is that the reason I wanted to make room for all of this here is I want you to see that we don't know the number of successes, but we do know the number of observations. We know that we have 19,136 observations. But you know what? We really do know the number of successes. We know that we have 29.2%, so you would have to take 0.292 times the 19,136. So you're going to have to do that on your calculator. When I do that on the calculator, I end up with 5588. So again, your number of successes, your P, number of successes needs to be calculated on your calculator in order to use StatCrunch. So going back on to the rest of this, it's automatically defaulted to a hypothesis test. Our null hypothesis is that the population proportion is 0.3. We are testing and saying that it's less than, so you're going to have to change that. And notice this already changed to 0.34. So that's really all I had to do, is I had to put in those four things, and I'm going to click compute. We ended up with a lot of the same information that we had before. We have a z-score of negative 2.41. We've got our p-value of 0.008. So that jives with what we came up with here. Oops, I'm really off the screen here. Jives with what we came up with here. Okay, now the last thing that I need to do in StatCrunch is this confidence interval. And I do want to show you something you need to be aware of. I can go into Options. I'm going to go back to Edit. I've got all the same information. I don't need to change that, but I need to deselect my hypothesis test and tell StatCrunch that I'm doing a confidence interval. But again, I'm going to have to change this confidence level to 0.9 because a confidence interval is a two-tailed event, and I need to choose a confidence interval where I have 5 in each tail, and that would be a 90% confidence interval. StatCrunch isn't going to know to change that. You will need to do that. So then I will hit compute, and we ended up with the same interval that we had right there. And we can see that 0.3 is not included in that. I might be off just a little bit. This is based on how StatCrunch is rounding versus how you're doing it with your calculator. Okey-doke.